So the next step in our discussion of uh, polar coordinates in general and polar graphs in particular is to think about graphs. What if I start off with an equation like this one, r equals 3, what does that look like? Right, if I try to graph this on my new polar graph paper. Well, we don't have a lot of fancy techniques for doing this yet, so I'm really going to just apply the old-fashioned approach that we use with rectangular coordinates and pick some points, right, and see where we end up with. So I'm going to start here. I'm going to make a little table, and I'm going to pick values of theta and calculate the corresponding values of r. Okay, so now let's start at the obvious point, right? When theta equals 0, r is 3. When theta equals, I'm just picking numbers here, right? When theta equals pi over 4, that's 45 degrees, r is 3. When theta equals pi over 2, r is 3. All right, so you see where this is going, right? If I pick any angle, theta, r is always going to be 3. So let's plot these points. I'm going to do an angle of 0, and I'm going to go over 3. I'm going to do an angle of pi over 4, 45 degrees, and out 3. Pi over 2 is 90 degrees. And I'm going to keep going, right? Pick any angle you like here, and r is going to be 3. So hopefully you see what shape we're getting here, right? This is the polar equation of a circle. It's one polar equation of a circle. It's one. There's actually, and we kind of saw this a little bit in the last lecture, right? There are different ways to do a circle in polar equations, but this is one of them. Okay, so how about this one? Theta equals pi over 3. Well, I'm going to do this using a table again, right? But this time, why don't you take a second, see what you come up with, plotting some points. Okay, so this time I'm going to kind of go the other way because I have a formula, very simple formula, but a formula for theta. So I'm going to pick values for r. Excuse me. I'm going to pick values of r and get values of theta. All right, so when r is 1, theta is pi over 3, 60 degrees. When r is 2, theta is pi over 3, 60 degrees. When theta is 4, or when r is 4, theta is pi over 3. And same thing is going to happen if I pick negatives. Right, if I pick negative 2, theta is pi over 3. So let's plot these. Right, pi over 3, that's this line here. Right, sorry, that's 30 degrees. Pi over 3 is this one, 60 degrees. So if I go out 1, I get this point, and there's 2, there's 4, negative 2 is this way, right, somewhere over here, and every r value I pick is going to give me a point on this line, right? I'm going to just kind of cut to the point. This is the polar form of a line. Specifically of a line passing through the pole that has, if you kind of flash back to our rectangular coordinate terminology, it has a y. This would be the equivalent of a line having a y-intercept of 0. Okay, so this one's a little more complicated. Right now we really do have a mixture of r's and thetas going on here. But I'm going to handle this the same way. I'm going to pick some points, right, and see what happens. I'm going to pick values of theta and get values of r. So I'm going to put theta first. And because I'm solving for r, I really am going to solve this for r. Let's divide both sides by cosine theta. And we get r equals 2 divided by the cosine of theta. Okay. So let's see. Let's start with 0. And when theta is 0, this is 2 divided by 1, which is 2. Okay, good. That's a good start. If we do pi over 6, that's 30 degrees. Cosine 30 degrees is the square root of 3 over 2. So that makes this 4 divided by the square root of 3, and my calculator tells me that 4 divided by the square root of 3 is 2.3. So let's go up again, right? I'm sticking with the angles that I know, at least for now. Pi over 4, cosine pi over 4, that's the square root of 2 over 2, which means this is 4 divided by the square root of 2, which again, right, referring to my calculator, this is 2.8. And let's do one more. I'll tell you why I'm only going to do one more in a minute. Pi divided by 3, that's 60 degrees. That's cosine of pi over 3, it's a half. So this is 4 divided by 1, which is 4. And now here I'm going to kind of stop, right? Because if I go higher, the next angle that I know the cosine of is pi over 2, and I can't do that because cosine of pi over 2 is 0. Then I get 2 divided by 0, and I'm in trouble. But that does kind of tell me what's happening here, right? As these angles approach pi over 2, the radius is approaching 2 divided by 0, which is, I hate saying infinity. Infinity's not a number. Can't be infinity. It's undefined. But it's getting really large, right? So as theta approaches pi over 2, the r values get increasingly big. So let's see if I can't get these numbers on here now. I'm going to go over, I'm going to start with 0, do an angle of 0, go over 2. Then when I do pi over 6, it's just a little further than 2. When I do pi over 4, again, the pi over 4 is kind of in the middle here. Again, it's a little further than 2. When I go to pi over 3, that's, in case you're losing track here, this is the pi over 3 line. This is the pi over 6 line. When I go to pi over 3, I get 4, which is out here. That's really weird, but do you see what's starting to happen? Right, first, just let's fill something in here. If I picked negative angles, what would have happened? Remember, the cosine of negative theta is just the cosine of theta. So if I picked negative angles, I would have been getting the same values, right? I would get the same numbers out. Okay, but what happens, because that's kind of the next obvious thing to ask yourself, right? So the next thing I would say is, okay, well, what happens if I go past pi over 2? Right, kind of skip over pi over 2 because it's undefined there. Skip past that and go to what would be next? 2 pi over 3. Well, if I do that, I'm going to get 2 over cosine 2 pi over 3. That's 2 over negative a half, which is negative 4. Now if I go to pi over 4, I'm going to get 2 over negative square root of 2 over 2, which is negative 4 divided by the square root of 2. Not pi over 4, 3 pi over 4. And then what's the next one? 5 pi over 6. That's going to be negative 4 divided by the square root of 3. Right? I'm getting the same numbers, but negative. Right? So when I go to 2 pi over 3, that's this line. I'm going to get negative 4. Make sure I stay on that line, right? I'm going to get this point here. For 3 pi over 4, I'm going to get something that's just a 2.8. It's almost 3. And then at 5 pi over 6, I'm going to get just a little more. Now, give or take my admittedly somewhat sketchy artistic ability, right? If we play the connect the dots here, we get the equation of a vertical line. Very strange, right? This is really a very strange result. We've become so accustomed to getting periodic behavior, cyclic up and down behavior from the cosines and sines. Here, all of a sudden, we get this straight line, right? Kind of a very unexpected result. That is the nature of these polar graphs, right? You get a lot of very unusual, occasionally very interesting, sometimes very aesthetically, very visually appealing kind of results, which is another one of the great benefits of working with this new system. We can get graphs, we can get behaviors and describe behaviors that we really couldn't with our regular rectangular coordinates. Okay, so we're not going to spend a whole lot of time talking about polar graphs. There is one more thing I want to talk about. These polar graphs, we've seen a little bit of this on the things we've seen so far. They have symmetries, just like our rectangular graphs had symmetries. And there are some rules for identifying them, just like the rules that we had for rectangular graphs. And that's what we're going to talk about in the next lecture.